Welcome back to Chemical Engineering Thermodynamics. We have now reached Lecture 2 in Unit 2, one of my favorite topics, which is entropy. So let us just dive into this module. So this is what we'll be covering. We're going to learn how to describe typical thermal systems and their system relationships, be able to calculate entropy for open systems, relate the second law to heat engines, and apply third law to the solution of chemical processes and problems. We're also going to justify the use of the zeroth law, which you have met in Unit 1 as well. So let us begin. So let's first start with the Kelvin-Planck statement. So what this really is saying is that it is impossible to convert all the heat extracted from a hot body into work. Additionally, in the heat engine, the working substance takes the heat from the hot body and converts a part of it into work and gives the rest to the cold body. Additionally, there is no engine that can convert all the heat taken from the source into work without giving any heat to the sink. So this means that obtaining continuous work, a sink is necessary. So I know a lot of these statements which I just read, it does sound like common sense, and you can probably think of practical examples of this. Now let's examine Clausius' statement. So what Clausius also said is that it is not at all possible to transfer heat from a cold body to a hot body without expenditure of work by an external source. Now this basically forms the basis of what we call heat engines. So what is a heat engine? So a heat engine is a device that produces work. There are also devices that divert heat to produce work. And additionally, the simplest heat engines are a 4-stage cycle. And basically, the second law restricts what portion of the total heat that can become work. So now let's examine the cycle. So with heat engines, they basically provide us with a classical approach to understanding the second law. Now, there are devices or machines that are able to produce work from heat in a cyclic process. So let's look at some of these. So receiving heat from a high temperature source, such as solar, an oil furnace, or even a nuclear reactor. Then it's going to convert a part of this heat to work, usually by, let's say, rotating a shaft. Then the waste heat is basically rejected to a lower temperature sink. So this can be the atmosphere, a river, etc. So remember, a heat sink is a large source that when you expel heat to it, it doesn't really cause that much change in whether the temperature of that system, right? And of course, this will continue in a process cycle. So let's examine it here. So we have the figure. So we're gonna start at Q in. So basically at Q in, let me see if I hope you're able to see my cursor. So at Q in, we basically receive heat from a high temperature source. So remember the previous examples, which are solar, oil, nuclear reactor, whatever the energy source can be, right? Then it's going to now convert a part of this heat energy to work. So in this example here, we are, let's say, using the steam generated from the boiler to drive the shaft, right? So it's rotating the shaft, okay? Then if you notice, we have W out. So it's going to reject the remaining waste heat to a lower temperature heat sink, which is by our Q out, which is where our condenser is. Then after that, the process will start again because we'll have, let's say, this liquid coming in, we have our work coming in for our pump to now pump fluid, which will be water in this case, to our boiler. We have our energy source here, and the process begins again. So let's recap. So all heat engines involve the following: absorption of heat into the system at high temperature, then rejection of the heat to the surroundings at a lower temperature, the production of work. So in the previous example, we saw that the production of work here by our turbine. We also have, let's say, the working fluid absorbing the heat from the reservoir to produce the net work, which would be W in our case, before discarding QC, which is our waste heat, to a cold reservoir and then return to the initial state. So in other words, we have that our net work would basically be equal to the heat, the difference in heat from our QH and our QC. So our efficiency now, so remember this symbol represents efficiency, would be our network output divided by our heat absorbed, which is this case here, QH. So we have our network output here, QH minus QC, divided by our QH. So these are different ways in which you can now go ahead and calculate the efficiency of our system. So what does it mean to determine the upper limit of our thermal efficiency? Right, so I want you guys to go ahead and figure that out. All right, so let's look at our degree of reversibility. So in order to do that, we're going to examine our Kernel engine. So the Kernel engine is a special engine that operates in a reversible manner. So I want you guys to, if you have forgotten what reversibility is all about, you can go ahead and review that lecture that we had mentioned, reversibility. So you can take a pause now and go back to your book or to your notes and figure out or to revise what is a reversible reaction, right? So a reversible process. So I want us to now look at the Kernel engine. So in the videos that are on our class website, there was a very good discussion of the Kernel principle and about the scientist Kernel as well. So I want you guys to make sure that you have watched all those videos prior to moving on. So in the Kernel cycle, there are actually 4 steps. So I want us to just quickly go through those steps of our Kernel cycle. So the first one, we have a system at a temperature of the cold reservoir, TC, and it's undergoing a reversible adiabatic process. So you guys remember what adiabatic means? There's that constant temperature process that causes its temperature to rise to that of a hot reservoir at TH. So they're basically in contact, right? So for step 2, the system maintains contact with the hot reservoir and undergoes a reversible isothermal process in which heat is absorbed, which is our QH, from the hot reservoir. So for step 3 now, we have the system undergoing a reversible adiabatic process in the opposite direction of step 1. And that brings its temperature back to that of the cold reservoir at TC. So it goes back to our initial temperature TC. So at step 4, however, the system maintains contact with the reservoir at TC, and it undergoes a reversible isothermal process in the opposite direction of step 2. And that returns it to the initial state with a rejection of QC to the cold reservoir. So guys, I want you to go ahead and watch back that video, because you can also now practice drawing that diagram that demonstrates Cardinal Theorem. So I will also go through it in the tutorial as well, which is a beautiful diagram that you can help you to remember the different stages of Cardinal Theorem. So let's now discuss Cardinal Theorem. So any reversible engine that operates between two heat reservoirs is called a Kernel engine. So what is a theorem? For two given heat reservoirs, no engine can have a thermal efficiency higher than that of a Kernel engine. So the Kernel engine is basically the most perfect engine that is there. So proof of Kernel's theorem assumes that the existence of an engine with thermal efficiency that is higher than a Kernel engine. So now this is a diagram here that is basically demonstrating our Kernel theorem and our Kernel theory. So we have our hot reservoir at TH, our cold reservoir at TC. And in between them, we have our, let's say, our initial state and our final state, and coming back to our initial state at our TC. So remember, the Kernel engine is actually the most perfect one. So let's look at Kernel cycle for ideal gases. So before moving on, guys, I need you, just like how we have this diagram here that is showing the process, the movement of the process between QH and QC and the different temperatures involved, which is our TH and our TC, coming back to our TC. All right, so this is our cycle. So from B to C and D to A, these are our isothermal steps, right? And for our Kernel cycle for ideal gases, we also now have to take into consideration our R, or gas constant, and our TH, right? When we're looking at our Q for our hot process. For our QC, we now have to take into consideration our TC.